Okay. Hold on, let me start my own timer. And then I'm ready.
Go right ahead.
Okay. How healthy do you consider your diet to be? Maybe you eat a lot of vegetables or a lot of protein. Maybe you limit carbs or calories or sugar. Some of these choices are healthier than others, but one key factor of nutrition is that supplements are almost never better than the real thing. Hi, my name is Aditi Gupta. I'm from Ridgefield High School, and today I'm going to be talking to you about my research on the impact of artificial sweeteners on hunger perception and consumption in Drosophila melanogaster. I'm going to start off by detailing a key neurological pathway in the food consumption process, the mesolimbic dopamine system. Stimuli like food and drugs trigger the release of dopamine from the ventral tegmental area, shown here in yellow, and signals are then sent to the nucleus accumbens, shown here in purple, which causes dopamine levels to rise. In the NAC, behaviors are reinforced. The mesolimbic dopamine system is activated by the consumption of natural sugars, such as sucrose. Studies have demonstrated the dopamine reward system's lack of response towards sucralose, an artificial sweetener, meaning that the consumption of artificial sweeteners does not activate the mesolimbic dopamine pathway in the same manner as natural sugars. We now know that eating sucrose leads to a dopamine increase in the brain. But what else happens when you eat sucrose? Sucrose, or table sugar, is produced naturally in plants. It's a disaccharide that is hydrolyzed by the enzyme sucrase and broken down into its component monosaccharides, shown here, glucose and fructose. These sugars travel through the bloodstream, and insulin allows glucose to be taken into muscle, liver, and fat cells, where it is then used for energy. The consumption of sucrose stimulates the neurological mesolimbic pathway. The resultant dopamine increase in the NAC leads to repetitive consumption of sucrose in an attempt to chase that positive dopaminic response. Now that we know about sucrose, we can start exploring the role of artificial sweeteners. Artificial sweeteners are highly popular sugar substitutes or alternatives, providing sweetness far greater than natural sugars. Funnily enough, nearly every artificial sweetener was discovered purely by accident because someone in a lab tasted a chemical compound that they weren't supposed to. So these potentially fatal mistakes became the man-made compounds that are today used in foods, beverages, dietary products, drugs, and even hygienic products like toothpaste and mouthwash. Artificial sweeteners are viewed as a way to achieve the same sweetness as natural sugars without any of the calories. Because of their low-calorie nature, artificial sweeteners do not provide energy. Their consumption does not lead to the production of ATP. Artificial sweeteners are divided into two categories, nutritive and non-nutritive. Nutritive sweeteners contain more than 2% of the calories in an equivalent amount of natural sugar. The only currently approved nutritive artificial sweetener is aspartame, shown over here on the left, and it's about 200 times sweeter than sucrose. During the digestion process of aspartame, methanol, aspartic acid, and phenylalanine are released. Every other approved high-intensity sweetener is non-nutritive, meaning they all contain less than 2% of the calories in an equivalent quantity of natural sugar. Sucralose, shown here in the center, is a trichlorinated disaccharide. So to make it, sucrose, the natural sweetener, is modified through chemical processes that replace its hydroxyl groups with chlorine atoms. This sets sucralose apart from the larger pool of artificial sweeteners. It's derived from real sugar, and it is 600 times sweeter than sucrose. Acesulfame potassium is composed of a combination of acetoacetic acid and potassium, and it's approximately 200 times sweeter than sucrose, and it's shown over here on the right. It's important to note that both sucralose and acesulfame potassium pass through the body undigested. So the scope of my research is to use all of this information to determine how artificial sweeteners impact consumption. I hypothesized that if Drosophila melanogaster is presented with food containing artificial sweeteners and foods without artificial sweeteners over periods of 1 and 3 days, it will consume larger quantities of the food with added sweeteners because of a subsequent stimulation of a neurological hunger response. So I knew I wanted to measure how much artificial sweetener the fruit flies were eating. What I didn't know was how exactly to do that until I came across an article describing the capillary feeder assay, or the CAFE assay for short. It involves the use of glass capillaries to deliver liquid food to Drosophila. The flies fly up to the exposed rims of the capillaries in order to feed on the liquid food. So the first step of my experimentation was making my sugar solutions because I couldn't just present my flies with solid powder and call it a day. So I combined sucrose with distilled water to create the stocked sucrose solution, which is the most basic food given to fruit flies in an experimental setting. This sucrose solution was divided into 4 equal portions and kept in separate containers. One of these containers was set aside to serve as my control sucrose solution. I then added 1.5 grams of aspartame, acesulfame potassium, and sucralose into each of the 3 remaining containers. These were my experimental groups, or my 5% artificial sweetener solutions. Next, I began the café assay. I put 8 flies into 4 fruit fly culture vials, 1 for each sugar. I plugged these vials with foam stoppers containing 6 glass capillaries each. Capillaries are essentially very tiny glass tubes that hold liquid without allowing it to spill. Each foam stopper had capillary tubes with a different type of sweetener, filled to a 50 millimeter mark. The ends of the capillaries were exposed to the flies in each vial so they could fly up to the rim and eat. So the café assay let me quantify the consumption of each sugar by allowing me to measure the decline of the capillary meniscus, and that is shown here in this image in the bottom right. As food is consumed, the meniscus level goes down, and this decrease represents the amount of liquid food that is either consumed or evaporated. I set up a vial with sweetener capillaries but no flies to allow me to subtract that decline and determine how much of the decrease in my experimental vials was due solely to consumption. So I performed 3 one-day trials and 3 three-day trials. For my one-day trials, I measured the capillary meniscus decline after 24 hours and recorded that data. For my 3-day trials, I measured the decline after every 24 hours for a 72-hour time period. And each time that I measured this decline, I replaced all of the old capillaries with new, fully filled capillaries to make sure that starvation was not a factor in my experimentation. One thing to note is that I initially didn't have 3-day trials as a part of my methodology, but after I performed 2 of my one-day trials, I realized that there might be a pattern in the difference in sweetener consumption between the first and subsequent days of exposure to this new sweetener, so I adjusted my methodology to include the 3-day trials. Here are some sample data tables that are indicative of the data I was collecting throughout my process. First, I'd measure the decline in millimeters, then convert to milliliters, then divide by 8 to get milliliters per fly. I discovered that Drosophila melanogaster consumed up to twice the amount of each artificial sweetener as it did sucrose, finding a 68.09% increase in acesulfame potassium consumption, a 93.75% increase in aspartame consumption, and a 61.84% increase in sucralose consumption. This all confirmed my hypothesis. The graph on the left over here is a visual representation of consumption of each sweetener over a 24-hour period, and the graph on the right represents consumption over the course of 3 days. You'll notice that the bar representing aspartame is significantly higher than the bars representing the other 2 artificial sweeteners. This might be because aspartame is the only nutritive artificial sweetener present in the study. In terms of its caloric weight, its consumption most closely mirrors the experience of consuming and metabolizing sucrose. Since this process was so similar, aspartame was more frequently and greatly consumed in order to stimulate the dopaminergic rush that the Drosophila associated with sucrose consumption. Now, I'm going to call back to how I adjusted my experiment to include 3-day trials to measure a difference in consumption between days. Turns out that didn't really matter, as these graphs depict. Through the Pearson's correlation coefficient test, or finding the R value, I determined that there wasn't really a strong correlation between the day and the amount of each sweetener consumed. So I used a 2-sample, 2-tailed t-test statistical analysis to assess whether the difference in mean observed consumption of sucrose and each of the 3 artificial sweeteners was of statistical significance. This t-test is commonly used to compare the means of 2 groups in an experiment with the purpose of determining whether a certain treatment has an effect on the sample. And I used Welch's test because of the differences in variances between sucrose consumption and the consumption of the 3 different sweeteners. The test was set at an alpha level of 0.05, and I conducted it 3 times, 1 for each artificial sweetener. This analysis yielded large t-values, so all my t-values were greater than 1.96, and then I used these t statistics to calculate p-values, all of which were less than 0.001, establishing statistical significance and validating the results of my data collection. Now, you might be wondering, why is any of this important? Well, The fact of the matter is that artificial sweeteners are everywhere, and they are becoming a new norm. They are particularly popular among those attempting to lose weight by means of a low-calorie diet or those with diabetes. Consumers eat artificially sweetened items while they're under the impression that they are taking action to prevent themselves from experiencing the harm associated with natural sugars.
2 minutes.
But in fact, they are simply putting themselves at greater risk of experiencing far worse ailments. Artificial sweeteners have been linked to various forms of cancer. They've been linked to obesity, heart disease, and various forms of cardiovascular diseases. Ingesting these sweeteners only increases one's risk of experiencing any of the multitudes of harmful conditions they've proven to be associated with. Despite the glorification of their low energy, high reward quality, it's highly probable that they pose a greater danger to human health than the natural sugars they promise to be superior to. My research provides valuable new insight into the dangers of artificial sweetener consumption. There are also some interesting economic implications of these results. Since you eat more artificial sweetener than you would natural sugar, you purchase more and demand increases. This is something I'd love to explore further in a future study. I'd also like to modify future experimentation to address some of the limitations of this research. I was in a biosafety level 1 high school lab, so my sample sizes were restricted simply because of the amount of space I had. I'd also love to incorporate a sensitive weighting methodology into my experimentation. I'd use a highly sensitive scale to mass each fruit fly before and after 24 hours of sweetener consumption, and this addition would assist in the verification of the quantity of consumption measured by the CAFE assay. And finally, I'd love to study this topic in a more complex model organism like mice or some other form of vertebrae. I'd like to acknowledge my mentor, Ms. Karamia Cologne, who's a chemistry teacher at Richfield High School, and she assisted me in ensuring my research could be conducted within the bounds of what was allowed in my high school's lab, and her guidance was invaluable. Thank you so much for your time. I hope you found my work as captivating as I do.